Hello everyone, Mr. Eck here. This is going to be just a quick video. I knew that I was going to write up solutions to this algebra of quadratics and parabolas worksheet, and I thought I'd record the solution procedure in case you wanted to hear me talk about it. The first problem asks us to just label the parts of a parabola. So this point at the top is going to be the vertex. In this case, the parabola is opening downward, so the vertex is a maximum. This point right here is the y-intercept, which can be also found by inputting f of 0, that is plugging in 0 for x. And these points down here are the x-intercepts, or I will most often call them zeros. 0. And these can be found by finding the x values that make f of x equal to 0. Finally, the axis of symmetry is this line right here. And it can also be found, or its x-coordinate can be found, by computing negative b divided by 2a. So we have vertex, y-intercepts, x-intercepts, and axis of symmetry are the key qualities or points that you might need to find on a quadratic function or parabola. Just over here, a quick word on the forms. I've just listed these here for you. Most of the times you're going to get a quadratic in this first general form, and usually you'll want to put it into that vertex form. Once it's in vertex form, this is a better form because it's easy to find the vertex, and it's easy to find the zeros because you can just solve for x. This is actually a better form. So you almost never go from vertex form to general form. That never makes sense. And then with factored form, one key observation that we make later in the sheet is that these C1, they use C here because these are complex. That is, they can be real or imaginary. Or both, a mix of each. So when we use C there, we mean like real or imaginary. And then this A coefficient, which is in all of the forms, that's actually a real number. All right, jumping over to problem 2. Without graphing, what's the equation of the axis of symmetry? Well, I know that the axis of symmetry is the same as where the vertex lives, so it's going to be at negative b over 2a. So I can compute negative of negative 30 over 2 times positive 5. So this is my a, b, and c. And that gives me positive 30 over 10, or 3. So the equation of the axis of symmetry will be x equals 3, which is a vertical line, as all axis of symmetries should be. Part B. What are the x and y coordinates of the vertex of this new parabola? So the first thing I'll compute is the x coordinate, negative b over 2a, or negative 6 over 2 times 3, which ends up being negative 1. So the x-coordinate of the vertex is negative 1, and then I'll just plug in to find y, I'll plug in negative 1. You get 3 minus 6 plus 5, or 2. So the coordinates, negative 1, 2. All right, for this next question, it's actually pretty much the same as the previous questions, just with a different variable and a different context. A ball is launched directly upwards. We know its height above the ground in feet after t seconds. So at what time is the ball at its maximum height? Well, that's going to be where the vertex of the parabola is. And the vertex is at negative b over 2a. In this case, though, it's not going to be an x value. It's a t value because t is the input variable. So it's going to be negative 80 over negative b over 2a, so that's 32. Can dig up our calculator. I think that's 2.5. Yep. So at negative 2.5, nope, not negative 2.5. I forgot a negative over here. Right, negative 16 is the a, so that should be negative 32 down there, which means the vertex is at 2.5 seconds. So that will be the time that the ball is at its maximum height. Because if we have a graph of height over time, and it's starting at a certain height of 6 and then going up, and then back down, well, where is it going to be a maximum? Negative b over 2a. Now to find the maximum height of the ball, just take that value and plug that thing in. It's going to be about 106 feet. So I'll just say it's h of 2.5, which is 106. And that's it. That's all you need. This next question is about the link between the factors and the zeros of f. So f of x has zeros at x equals 5 and negative 2. So if I know that I have a 0 at x equals 5, I know that f must have a factor of x minus 5. That's just the factor theorem in operation. And if I have a 0 at x equals negative 2, then I need a factor of x plus 2. And then to make an equation for f, we can just multiply those together. So that would be something like y equals x squared minus 3x minus 10 as a possible equation for f. Now, this is mentioned in the notes here, but you could also have other equations for f, like y equals negative x squared plus 3x plus 10. That's another possible equation for f. Or y equals 2x squared minus 6x minus 20. Those are all possible equations for f because multiplying by a scalar in the front, a coefficient in the front, doesn't change the zeros. It just stretches or reflects it. But if this is just saying what is any possible equation, it's probably best to stay simple and give the thing just based on the factors. There are other problems that will talk about initial conditions that you might have to add a multiple in the front or something. But you do that as the last step whenever that happens. And you can play the same factor game with imaginary numbers. So if we have a 0 of x equals negative 7i, then we must have a factor of x plus 7i. And if we have a factor of 0 of x equals 7i, then we must have a factor of x minus 7i. When you multiply these out, this is a conjugate pair, and they multiply just like x plus a, x minus a. So this is going to multiply into x squared, and the middle terms will cancel out, and we'll get minus 49i squared. But I squared is equal to negative 1. So really, we have x squared plus 49 as the simplest answer there for a possible equation for f. And you could, of course, multiply that by 2 or 10 or some other number if you wanted to, but that's the base equation that's going to have those zeros. Okay, next one. This does get a little more algebraically interesting. So when you write the factor for a 0, remember that this is the number part, and you still need to do x minus that number, because that number is part of the factor. So this is the factor, and here we have x minus 1 plus 3i. So we still have things of the form x minus c, x minus c. And now we're going to distribute the negative. But it's that messing up the negative is where a lot of people get confused. And when the problems start to have multiple terms like this, like a lot of times folks will just think, oh, conjugates or something, and they'll make that the plus. Then it doesn't work anymore. So make sure you're staying honest with the factor theorem, I should say. So then this is the same as x minus 1 plus 3i, x minus 1 minus 3i. And the best way that I like to multiply these is with a box. collecting all the like terms here, we get the equation x squared minus 2x plus 10, which is right, y equals x squared minus 2x plus 10, as a possible equation. And notice that all of the terms with an I ended up canceling out, because eventually our quadratic will have only real value coefficients, even if you get in various imaginary 3i and 3ix terms. But what doesn't cancel out are the minus x's, and also the minus 9i squared becomes 9 and then adds to 1 is where they get to 10. So that's where the algebraically difficult part comes in. You could check your work, by the way, by plugging this thing like into the quadratic formula, and you would get, if you did, these as your imaginary zeros. Here's that work, by the way. Just quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. You get a negative under the root, but it simplifies to 6i, and then the 2 reduces out of all of the terms, and you get 1 plus or minus 3i, which are the zeros we started with. And then the last piece is just an observation about imaginary zeros, which is that if a polynomial, not even a quadratic necessarily, but any polynomial has imaginary complex zeros, it will never just have a single one. They must come in conjugate pairs. The reason is that the polynomial started with real valued numbers. So if you have a single factor with imaginary numbers, well, that has to have a friend so that the final result has no imaginary numbers. Because you don't walk around and be like, oh, this x squared plus 2ix plus 3 is a counts as a polynomial. It doesn't. It has to have real valued coefficients. So this is really just saying, hey, if this is 1, 0, what would the other 0 have to be? Well, if the 1, 0 is 1 plus I, the next 0 had better be 1 minus I. If 1, 0 is 4 minus 2i, the next 0 had better be 4 plus 2i. If 1, 0 is 13i, the next 0 had better be negative 13i. And if you want to put the real parts in there, it can be 0 plus 13i and 0 minus 13i, but you don't really need them. And then the last one's tricky, because I bet a lot of people will think it's going to be I plus 6, but that is wrong. I plus 6 is really negative 6 plus I, so the imaginary complex conjugate is negative 6 minus I, and if you want that to be a good 0, that's what you're going to need to have. So be real careful with that last one, that you don't just flip the sign, you actually think about changing the sign on the I term if you want this to work out nicely. Well, folks, that's it. That's all I've got for you. Please bring me your questions on this worksheet later. I will post the entire worksheet to our classroom, and I'll see you in class.